Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number... Time series problems are everywhere. For example, as you'll hear today, predictions about parking occupancy and traffic can be done, which might prove useful to urban planners, emergency response teams, and a variety of other public and private parties. If you're interested in making time series predictions, surely you want to use the most powerful algorithms in pursuit of the best model, right? Today on the show, I explore that question with Shereen Elsayed and Daniela Thyssens, as we discuss their paper, Do We Really Need Deep Learning Models for Time Series Forecasting?
My name is Shereen Elsayed. I studied my master's in University of Hildesheim, Germany, and now I started my PhD just like this month.
Oh, congrats.
Yeah, thank you. That's it. I think I'm from Egypt. I've been living here for 3 years.
Yeah, basically it's the same for me. My name is Daniela Thyssens. I'm currently also a PhD student at Information Systems and Machine Learning Lab at the University of Hildesheim in Germany.
So the paper I invited you both on to talk about today is titled, Do We Really Need Deep Learning Models for Time Series Forecasting? Maybe to kick off, I'd love to ask you both a little bit more details about your backgrounds. I know time series is something that not just machine learning people have done for a long time, so there's a multidisciplinary set of methodologies that can be looked at. How did you both become interested in this area?
Well, it started with our project. During our master's, we have to go through a project for 1 year. So we selected the parking occupancy prediction. And this topic basically is also time. We considered it as time series forecasting. And from here, we started working together on the problem. And from there, we got to the paper of Do We Need Deep Learning Models?
Regarding our backgrounds, we're more on the general machine learning side, of which, of course, time series forecasting is a vital part in it and has recently been very much touched also from the deep learning side, which was also, of course, our way to go. Before we then found out that presumably simpler baselines also work well on this task. To come back to your questions on backgrounds, I do actually also have quite some background regarding time series forecasting in a different setting, since I already have a master's in quantitative economics, in which I of course had some finance classes. And so this project, as Shereen mentioned, just also came natural for me as a topic to choose.
Time series forecasting is a pretty long-term topic. It's been around for a while, maybe even longer than I know, with a lot of different techniques and approaches. Could you talk a little bit about the breadth of things? I'm sure ARIMA will come up, but anything else you want to share that helped or was useful, or the sort of non-deep learning techniques that were interesting from a time series forecasting perspective?
Yeah, there are basically a lot of techniques that were used, statistical methods, and ARIMA for sure, rolling window, and these basic techniques. Repeating the naive method is only repeating the lost values for a long time, and this is, despite it is very naive, but sometimes in some time series forecasting problems, it shows a very good results because, for example, if the value is already repeating itself, so repeating the value will give a very good prediction into the future. And you can just average the previous also period and predict it as the predicted values. There are several naive methods, statistical methods, rolling windows such as ARIMA and so on. Also going to the other machine learning methods such as GPRTs for sure, random forests and so on also could be used for time series forecasting.
And are you aware of any, I don't know if it would be a flow chart or a heuristic, but some way that people typically pick methods?
I would say it depends on the problem.
Yeah, I mean, from the time series or from the machine learning perspective here, what people mostly do is just look at the state of the art, and mostly what people will see there is that LSTM models, RNN models, all of these recurrent network models that are built basically on sequence type data are, of course, the method of choice for most people, as they see from the current state of the art that this is a very competitive and a good state of the art approach.
Yeah, even matrix factorization is also used for time series forecasting sometimes, but it has its drawbacks as well because it only finds the linear relation in the time series, which is not the case all the time. But I would say if someone who doesn't know state of the art models or so will go for something like ARIMA because it's the simple basic.
Yeah, and it's very applicable. I mean, if you just type in Google time series forecasting model, the most recent, probably the most earliest convenient model that will pop up is mostly an autoregressive model such as ARIMA.
Models like ARIMA have a good intuitive sense, at least for me, when I think about, I don't know, maybe weather data or something like that. There's a natural variance, but also some periodicity to it. So if it's autoregressive, obviously yesterday is a good predictor of today's weather in some places, and the moving average as well, like is a nice way of smoothing it out. So there's a lot of really intuitive aspects that are appealing to me about ARIMA. What's the motivation then to move away and do something like deep learning where perhaps I lose interpretability?
The most interesting part is also the most interesting finding of our work is how you actually reformulate such an forecasting task as it is used plainly from ARIMA into a machine learning regression task where you actually don't give anymore the model the input of a complete and consecutive sequence that the model is then basically fit on, but actually translating this forecasting problem into a regression problem in terms of chopping the complete time series up and feeding to the model blocks of this time series. From then it then should predict the next horizon. So I think the strength or why people use deep learning or generally machine learning models with this type of problem is the translation to a simple basically regression problem.
Could you perhaps go into a little bit more detail about that feature engineering process and how you translate it into something that's maybe more familiar to a machine learning practitioner?
The main idea firstly came from that we wanted to simulate how RNNs and LSTMs takes the input to the GPRT as well, because basically we felt that it is a bit unfair for the GPRT that RNNs and LSTMs are trained on windows and then predicting a certain horizon from these windows, while the GPRT traditionally was used by taking the whole time series and then predicting the next testing period that we want to predict or to forecast. So in this case, the idea came that we want also the GPRT to take the input as windows as well. So doing that, we started to cut the data or the input time series into windows and then predict a certain horizon. So this is how we changed the input of the GPRT from being just naively feature engineered or whatever in this case to actually take the input as the RN and LSTM. Will it be competitive to these models? And actually this is what we found out.
Yeah, that's the core question. I want to get into the results, but maybe we should first talk about the data sets. It would be easy if someone didn't be on the headline to maybe dismiss it of, oh, you found one case, of course there's one case out there where some technique will shine over others. But that's not what happened here. You looked at a variety of different data sets and found pretty consistent results. Could you talk a little bit about the data sets you used during the experimental process?
Yeah, I think this is pretty easily explained. From the literature, we were first not looking at the datasets per se, we were more focusing on which new deep learning models we can use in our study. And it turned out that most of these recently published, very well known models featured the same datasets, which were most likely the univariate datasets such as electricity and traffic. And then just came naturally that if all of these models across and cross-reference these data sets even, we can just use this to build this study that we actually did in order to give this big overview of data sets and which are popular also in the research community. So it was more a natural coming thing to use these data sets.
When you identify some common, like canonical data sets like that, maybe electricity or traffic, if you want to zoom in on one or the other, what's it like to get started from the actual getting your hands dirty practitioner point of view? How do you get the data? What's its format? And, what are the steps to ramp up looking at something like that?
Yeah, I think this is a core thing that every data scientist or even machine learner should be aware of, that this looking at the data sets, how were they treated across models? Can we use it in the same way? Looking how long even or how big the data sets is, this is a core thing and it takes time, right? You need to check the data sets and clean it up, and this is done differently by different models. So of course you need to find a way through to merge it. And this is also one critical point we mentioned here in the paper, that why do researchers make it so hard to compare these models on the same data sets, even though they use the same data sets? It's very hard to get this comparison because some researchers will shorten the data sets, others will just make it longer by adding some variables to it, or not even being explicit about what they turn into the data sets. So yeah, this is definitely one point that took a lot of time for us, I think.
And what's the nature of those data sets? Once you kind of jump through all those hoops to get some reproducibility with what the researchers laid out, do you get just a univariate time series that has, 2 columns, a date, time, and a value, or what's the raw data look like?
Yeah, actually, this is quite it for at least electricity and traffic. These are the univariate data sets. So basically, in some cases, you don't even have a data timestamp. So you are just aware that the data is recorded every hour. Most cases, of course, you have the date and timestamp of it, and then you just have values, consecutive values, right? And you have this. When we consider electricity for multiple households, then you have the same electricity variable for multiple households at the same timestamp. This is it.
Well, one of the nice aspects of the paper that I enjoyed was the way I don't know if you'd call it a head-to-head competition or a benchmarking, but that you've explored a variety of algorithms and data sets and kind of put them all to the same tests. There's a lot of data points to go over in that report card, but broadly speaking, could we start getting into the results? What did you find in terms of performance?
Yeah, firstly, regarding the head-to-head setting, this was our main concern in the paper. We wanted to have a head-to-head comparison because it's best to compare against the published results, as they know their model. They tuned the model to give the best results. But if we tune their model according to what we see, we might not get the best performance of the model. But we wanted to make sure that actually, if we want to see the effectiveness, we wouldn't say proposed model. We would like, or we would prefer to say a proposed feature engineering approach. If you wanted to see the real effect of this method, we have to see the best in other models, not just make them weak and then show that we having good results. So that's why we insisted to try as much as possible to compare head to head with other results.
Yeah, I mean, from our standpoint, this is vital, right? Because who will believe us when we just create our own experimental setting against these prominent models and would then claim that a, so to say, simple machine learning baseline would be outperforming all of these really complicated deep neural networks. So starting off from the results, we can see that it is not such that our proposed baseline model based on the GBRT is greatly or overwhelmingly outperforming these great models, but is instead competing and is giving a valid baseline for these deep neural networks that we can say, yes, in some sense, we do see an improvement in those deep learning models over this baseline, but they are not that significant. And this is one strong point that we want to make throughout the results, is that people out there would need to choose stronger and more competitive baselines against which they do perform their experiments.
Thanks to this week's sponsor, Vertica. Vertica's ML-powered analytics is designed for pioneers. It's a truly unified platform. Vertica lets you keep your data where it is. Vertica offers cloud variety, giving you the flexibility to use multiple clouds, on-prem storage, or a hybrid or both, with the ability to read from different formats across all of them. With superior query speeds, sophisticated SQL analytics, and greater accuracy, Vertica gives you the power and performance to take your business to new heights. Vertica is built to adapt and provides the tools and agility to evolve with the future of analytics. Vertica is analytics for pioneers. Head to vertica.com/insights to learn more. There you can read how other data pioneers use Vertica to realize over 2.2 million in benefits through better business insights and less effort. That's vertica.com/insights. What are the metrics or mathematical techniques you use to decide the performance?
Yeah, we had different matrix. Initially, we had the RMSE, the root mean squared error, the WAPI, and the MAE, the mean absolute error, for all of the model. But then when we compared head-to-head, sometimes other papers have different matrix, such as, for example, the relative squared error or the correlation coefficient. So initially, we have these main matrix, the RMSE, the WAPI, and the MAE, and then we have other matrix depending on the paper we are comparing against.
And broadly speaking, can you talk about the spread of performance? Are the results very tight in that regard, or do you see the methodologies showing strengths and weaknesses on the different types of data?
Exactly. Yeah, that's what we see. We do see that this varies across data sets and across basically the forecasting tasks. Surprisingly, for a task like traffic prediction, where the data is pretty synchronous, right? We would assume that at some points in time there is just elevated traffic where just in the middle of the night there wouldn't be. So I think in these kind of more uniform forecasting tasks, we could say that, yeah, the results are similar and the gap is not so strong. But surprisingly, for tasks like electricity, we do see a pretty large variety. This could partly happen also to just the model being not habited to the current data set tasks at hand.
Well, the metrics you're looking at are certainly a great guide for when someone might be deciding what algorithm to choose for their particular data set if they're going down a path like this. But the metrics alone might not be all we want to consider. Are there other advantages to looking at non-deep learning models that might motivate someone to go in that direction?
Well, for one thing, I think they are just less complicated in the sense of computational effort and complicated implementation wise. I mean, GBRT in the way that we use it as an XGBoost implementation that is freely available and is very easy to apply. Our code is online, I think, and everyone can see it. It's, I think, like 100 lines of code. Whereas if you look at complicated deep learning models, you're of course headed for and if you want to re-implement that and understand how it works, then of course one should be pretty advanced also in terms of deep learning.
So in the simplicity, is that an advantage in terms of a simpler model is easier to implement, less prone to have bugs in it, maybe easier to understand and interpret, and perhaps also, as you said, computationally more efficient? Or are you kind of appealing to Occam's razor, that the simpler solution might be the more parsimonious one?
If you Google the advantages or the pros of the GPRT, you will find that it's exactly what you have said now. It is explainable, easy to understand, and easily to apply as well. But computationally, sometimes GPRTs take also quite memory size and computational power as well. Maybe, yeah, computationally, sometimes deep learning models can be computationally more efficient, while for someone who is new to machine learning or doesn't want to get deep into state-of-the-art models or complicated models, will basically choose something simpler such as GPRT.
Yeah, I think on one hand, it's also the case that you could ask the question, why getting more complicated when the results can also be achieved by a rather straightforward machine learning model. But we don't want to argue in our paper that deep learning is senseless or doesn't make sense in time series forecasting, but rather we want to challenge the way deep learning models are configured and maybe also challenge further or upcoming deep learning models for time series forecasting to just perform a more rigorous experimental setup where we do really see those benefits of deep learning over simpler machine learning models.
The notion of I'm guessing you're familiar with the transformer architecture and the attention mechanism that's become very popular in deep learning. I think for good reason, because it sort of, in my mind, intuitively fits with a lot of time series problems. Like you were mentioning earlier, that traffic in the middle of the night is, if you know the time and you know something about the context of the world, that yes, traffic shouldn't be very high at 3 a.m. And it seems like something like the attention mechanism should very quickly capture those ideas. But that's not the only methodology that can do it. Is it fair to compare and contrast something like attention mechanism with the flattening and window feature engineering technique you guys created?
Yes, as you said, transformer models are currently the new trend in machine learning, and they are currently used in all different fields, as we can see. And yeah, they should work, and they are definitely good for time series forecasting. And maybe our new version of the paper that we will upload soon, we are comparing already against a transformer model, which was recently presented in 2020, because maybe the newest model in the paper is 2019. So this model is proposed by Google, and it is actually beating the GBRT, which is what we expected and what we wanted to show. We wanted to show that, okay, these new methods and new techniques are definitely beating the usual state of the art or usual baselines like GBRT. And yeah, this makes a lot of sense.
I'd like to go back and revisit some of the reproducibility conversations we just touched on earlier. Having gone through the perhaps arduous process of getting all these models and reproducing many of them, do you have any advice for future researchers on how they can make their work more accessible to other people and more reproducible in a fashion like this?
Yeah, so I think the first idea is if the dataset is open source and has been published by one or two models, deep learning models for this case, that you want to compare to, then the best and naive way is just to use exactly that setting of the data with the same length of the time series, with the same number of features, etc. I mean, of course, what we might think of why one or two people were changing the setting is, of course, that it better fits for their model. So, of course, you want your model to shine most. And that's why you come about and configure data sets or change a bit of the data set. I mean, this speaks against of a fair head-to-head comparison, but on the other hand, it's also a way to make your model shine most, but it comes at the cost of changing the data set and make sure it works fine, newly fine-tuning it. All of this comes up with reconfiguring a data set and trying to run baselines on that.
Yeah, and also it is very useful to upload your code on something like GitHub or so.
We have, I think, a complete list in the appendix of works where either the dataset was not publicly available, which is sensible if the data is not something that is officially recorded or so, or it belongs to a company. But why codes or reproducibility information is kept from the people who want to re-implement it just seem a bit weird.
Yeah, and sometimes even adding an appendix to the paper with the hyperparameters, the best hyperparameters that they found is really important, because sometimes, okay, I might have the code, might have the data, but I'm not able to reproduce the results in the paper because I don't know the hyperparameters or the best setting of this model. But a reproducibility section in the papers is really important, plus the code and so on.
Absolutely, I couldn't agree more, especially code, with how easy it is nowadays to share on GitHub or other tools like that. It's almost suspicious when someone doesn't. I hope that becomes much more of a standard than it has been. Maybe we could put ourselves in the shoes of a data scientist or machine learning practitioner at an early but growing company, something like a retail company where they have inventory forecasting problems. Like they need to reorder goods before they run out, but not reorder too much because they have a limited warehouse. A pretty kind of classic supply chain optimization problem. Certainly, time series forecasting can be of great value to this person, but if they don't know their data set yet, do you have any advice on how to get started?
I think in this case, what is usually done is randomly generating a dataset while knowing, for example, what the distribution of the data could be. And they can, for example, randomly generate a data to see how could it be.
Or, you could already start off by, if you have a model in mind or a forecasting setting in mind, you could just start off with publicly available similar data sets. I'm currently not directly aware where I could point my finger to, but I am sure one could find data sets that simulate this type of data that one of those retailers would then generate in order to already train the model and see how it works. Until enough data, of course, has been stored and can then be tested on.
Well, let's, in our hypothetical, assume we've got a good, I don't know, whatever we need, 6, 12 months of solid retail sales data. And let's even just assume it's somewhat stationary, whatever that means. So it's not exhibiting some, rapid growth property or something. If I were just reading headlines, I might be inclined to say, I'm going straight to deep learning. Let me just get the latest and greatest. But your paper really inspires me to think, hey, perhaps I should consider more broad techniques or try a lot more and be experimental at the start. Do you have any thoughts on methodology selection in that regard?
So first of all, it depends on the data, I guess. If you are planning on having highly scalable models, then maybe, as one can see in our paper, some of these methods that we have shown in the deep learning area are meant to be for these highly scalable big data amounts, like the deep global local forecaster model. On the other hand, if you are new to this and you want to understand what the model is doing, and especially as we have shown GBRT is working well with external features, its performance is massively boosted by external additional explainable features. If you consider getting a lot of those features and configure them right, then there's nothing keeping you from trying an easier model like GBRT that you can maybe implement yourself, understand, and can also make reasonable predictions with.
Yeah, and if you are pointing to specifically the state of the art or the deep learning models that currently existed or that we have seen of great value that we compared against, I would say that there were two models that showed great performance and as well as great time consumption and so on. So the deep global local forecaster, as Daniela said, the deep glow, this model is really good and fast and of a very good performance, as well as the temporal fusion transformer that we have talked about recently proposed by Google. Yeah, these two models are really, really good models.
And are there any particular industries or types of data sets that you think might benefit from the wisdom conveyed here? In other words, should hedge funds be looking more broadly at techniques or...
What I was going to say was that as GBRT, as we shown in our study, has shown great value across a variety types of data sets, which also financial data sets belong to, builds a great, let's say, all-rounder, whereas many deep learning models focused on specific tasks. Most of them, I think, on traffic forecasting, for example. If we think about financial surroundings or working with financial time series data, then I think GBRT builds a great baseline. Any other model, I think, very, very well work probabilistic models like the deep AR and deep state space models that are also predicting variance and predicting the complete uncertainty quantification.
And I'd love to learn a little bit more about where each of you is headed next. Can you tell me about your current areas of research and maybe if it is a follow-on from this line?
Yeah, even my master thesis was about image-based recommender systems. So currently I am searching into the recommender systems area and next basket recommendation and so on.
Yeah, funnily, we both started off with, or we are headed basically for different machine learning tasks. I, for myself, are currently working on combinatorial optimization problems, including vehicle routing problems. So, on one hand, this paper is more than just working on time series forecasting. I think the message should be larger in the sense that this can be basically replicated for every field where we would assume that not strong enough baselines are delivered for these highly specialized tasks. So I think what we will take with us on our way forward is definitely this critical eye on selecting useful baselines that are meaningful.
Is there any place people can follow you both online?
We are both on ResearchGate. I think this is becoming more and more popular.
LinkedIn, right? Or Google Scholar.
Cool. Well, thank you both so much for coming on and sharing your work. This is a really interesting result, and I was glad that the paper came across my desk. That concludes this installment of Data Skeptic Time Series. Our guests this week were Shereen Elsayed and Daniela Thyssens. Claudia Armbruster is our associate producer, Vanessa Bly does guest coordination, and I've been your host, Kyle Polich.